All right, this is a review of problem 2B.8, analysis of a capillary flow meter. It has to determine the flow rate in pounds per hour through the flow meter. This flow meter, the fluid flowing is in an inclined tube. Water is at 20 degrees C, and the manometer fluid is CCl4, density 1,594 kilograms per meter cubed, and the capillary diameter is 0.01 inches. Notice measurements H and L are sufficient to calculate the flow rate data. Need not be measured. Why is that? Okay, so yeah, H is big H right here. And the reason that theta needs not be measured is because you can solve for L, or you can solve for this little h, and from that you can get theta, and that's because at point D and E, the pressures are the same, and as you'll see in the problem, that lets you get around knowing what theta is, because we'll get to that, but it's easier to just go through the problem and do it like that. Okay, so first we're just gonna do momentum balance and try to find the Hagen-Poiseuille equation for this system, which is just a mass flow equation. So first we're gonna do momentum shell balance, and for that we're gonna need a momentum flux in the ZZ direction, and that's because there is going to be a pressure in the Z direction, and that's going to be due to the Z direction because the pressure changes with vertical height, because that's in the direction of gravity, and there's going to be a velocity in the Z direction due to the radial direction, and the velocity is in the Z direction, and it's ZR because the velocity in the pipe is dependent on the distance from the pipe walls. So closer to the walls, the velocity is going to be closer to the wall velocity, and the wall velocity is 0 because the wall is not moving. That's just friction. When the fluid is at the surface, there's no movement. So we're assuming static friction completely stops the water at the water wall, or at the surface walls. So that's why, and that's like that's a laminar assumption. So because we're assuming the fluid is laminar, I don't know if it says that specifically, but oh yeah, laminar flow, I guess, chapter 2, laminar flow. That's where we can say that specifically. So yeah. So that's why we have these two. So for the momentum flux in the ZZ direction, this is like due to the Z direction, we're going to need the AZ face, which is the face and the face perpendicular to the Z direction, and that's this purple face on this model. So the Z direction is like this direction. Oh, so the Z direction is with the pipe. So the Z direction is this direction. So yeah, the VZ is also directly in line with the Z direction. So that helps out. Kind of forgot about that. So yeah, AZ is basically just going to be this big circle minus the smaller circle. So imagine the radius here at the inner edge of the circle is R, and then the radius at the outer edge of the circle is R plus delta R. So to get this area, you're going to need to subtract, or take the larger circle and subtract the smaller circle that's within it, and that's how you can get the area. So the larger circle is pi R plus delta R squared minus pi R squared, because area of a circle is pi R squared. So we're just doing some algebra, simplifying that out. And this term goes to 0 because it's delta R squared, and delta R is like an infinitely small value. Obviously from this picture, it doesn't look infinitely small, but when you're doing integration, it's like iterative over an infinitely small value. That's like the basis of integration and derivatives and whatever. So if you multiply an infinitely small value by itself, it's like infinitely small. So we can just cancel that out and say it's 0. So we get our AZ is 2 pi r delta r. And our face that our ZR is applied on is because it's dependent on the R direction. So we need the R direction. So the radial direction extends outwards from this center line. Obviously, you see the radius is extending outwards. So the face perpendicular to that radial direction is just like the cylinder itself. So it's 2 pi r, 2 pi r, which is the circumference of the circle times the length, which is obviously the length. So it's just the surface area of a cylinder, basically. And then the volume, you're going to need that because you need to apply the gravity is applied on the volume as a whole, not on the face like the momentum flux is. So you're going to need the volume of the differential. The volume of the differential volume, I guess. So it's like basically this purple and this pink face combined into one solid. So that's 2 pi delta r L. And that's this. It's basically you just take this AZ. Wait, does that make sense? Yeah, that makes sense. It should. Wait, it might be. I think it's 2 pi r delta r L. It's not 2 pi r just delta L. But I might have. Yeah, I didn't apply it here. I'm not sure. It's not applied. It should be. This should be 2 pi r delta r L, and that should be multiplied here. I don't know why it's exactly not. It should just be G sine. Or maybe it's rho G sine this, but it's not applied for whatever reason. And we're dividing by 2 pi L delta R and not the R because this RZ is dependent on R, so the VZ is going to be dependent on the R direction, so you can't just divide by R. And this is R plus delta R here within the parentheses, not outside. And that's because like this surface, this pink surface, like if you have a larger R value, like R plus delta R, the surface itself will also increase. So the surface will be 2 pi R plus delta R times L. I don't know. I'm not sure if that completely makes sense, but yeah, I guess I'm just going to continue on forward. So yeah, oh yeah, the sine theta as well. The sine theta is because gravity is it's in the vertical direction. So the z direction is this direction in our system. So if your theta is this direction, sine theta of z will be this direction, and that's the direction that gravity extends in. So that's how gravity is going to be applied. So that's why it's sine theta as well. That's why you're adding that sine theta on. Yeah, I think that's all I got to say about that. So yeah, normally for this equation here, this would be multiplied by 2 pi r delta RL, not 2 pi delta RL. There should be an extra R here. I don't know why I didn't write it at first. So yeah, but this dividing by just this and not R, that is correct. Or dividing this without the R is correct because VZ is dependent on R. Oh, or the volume without the R term. So I guess I did write it correctly here, but I just didn't write it correctly here. I don't know. There should be an R here. This is incorrect. This whole thing is correct, and this should be multiplied by the volume here, but it's not. But it, I don't divide it out here. I'm not sure. I'm not sure why. That's just kind of strange. Yeah, I don't know. So yeah, and I just leave this like this because these are just going to be pressure. This is just going to be modified pressures, so that's why I didn't put it in the derivative form. I kind of skipped some steps there. I don't know why. Well, maybe I just didn't do the steps yet, so let's just look. So momentum in the ZZ direction, that's going to be pressure plus tau ZZ plus rho VZ. From table B1, tau ZZ equals negative mu 2 dVz dz, and I can look at that, I guess. Yeah, tau ZZ was negative mu 2 dVz dz, and I just didn't write these terms because we're assuming it's a Newtonian fluid. If you read this, it kind of just goes through that. And this term just cancels out in general because the VZ velocity is not dependent on the Z direction. It's dependent on the radial direction because that's the direction that the walls extend. So yeah, tau ZZ this just goes to 0. And so you're just, these terms will cancel out in this momentum balance as well, because again, from this, we could say the velocities are not dependent on Z. So rho VZ at Z equals 0 will be the same as rho VZ at Z equals L. So the terms will just cancel. Yeah, so now momentum in the ZR direction, that's tau ZR plus rho VR. And again, you can notice that there's no pressure there, and that's because, I'll look at that. That's because of these equations, which show momentum flux when the symbols are different, it won't include the pressure, and that's because this like generalized form, if these symbols here are different, this sigma symbol will equal 1. Or if they're different, the sigma symbol will equal 0, so the pressure won't appear. But if they're the same, then the sigma symbol will be 1, so the pressure will appear. And these symbols are just like, it's just showing the same symbol and different symbols. So you could do YY, you could do ZZ, you could do, and in this case we do ZR for this one. ZZ. Generally look at these things. Don't really look at this. I mean, it's the same equation, but it's just, when I was doing these problems, it just makes it easier to understand what's going on, basically. So yeah, that's where we get that tau ZR, and then this term cancels because there's no velocity in the radial direction. If you go to table B1 to find tau ZR, tau ZR equals negative mu dVr dz plus dVz dr, and there's no velocity in the radial direction, so that term cancels. So tau ZR or RZ is just going to be negative mu dVz dr, and that's the conclusion I come to there. So now I'm just rewriting the momentum flux equations with the newly defined terms. So yeah, when you have like these pressures, you usually don't put it in a derivative form. Like you just write out the pressures, and this is pressure at Z equals L, and pressure at Z equals, or pressure at Z equals 0, and pressure at Z equals L. You usually don't write a derivative out for that. Like you don't write it out in kind of like this when it's just the pressure. And going up to this, well, actually, yeah, I guess I can kind of go back and kind of explain. I moved this thing over to the other side when I divide it by this volume minus r, because a derivative is out minus in, whereas the momentum flux shell balance is in minus out. So that changes the sign. So if you're wanting to convert to the derivative form, it's gonna add a negative sign. So with that, I just moved it to the other side so I can maintain the sign. I just moved at applying the derivative, switched the sign over, and then I moved the term to the other side so the sign remained the same as it was, but just it was flipping to the other side of the equation. So that's why this is on the other side of the equation now, and it maintains its sign. So yeah. Pressure increases the pipe as you go downward in a liquid. Pressure can be expressed as rho GH. And density times gravity times height, and that's in units of Pascal, which is something, I don't know. It's just units of Pascal is the SI unit for pressure. In the problem figure, we can see that the pressure at points D and E is equivalent, and that's because there are equal amounts of the same fluid beneath each of these points. Yeah, that's what I said. Using the equal pressures at point D and E, we could set the equation pressure at A equals P0. So I'm just saying this is equals 0 and this is equals L. With that, writing the equal pressure equation. So basically, what we want to do is find some way to relate the pressure on each side of the capillary flow meter here. So we're going to say at A, the PA is equals P0 and PB equals PL. So these pressures are due to the flowing fluid that's through here. And P0 is going to be greater than PL. So the fluid is going to flow in this direction because, well, you'll see later. But so a way we can do this equation is we can see that the pressure at D and the pressure at E are equal because they have an equal amount of the same fluid below them, which is CCl4. So we just need to find a way to calculate each of these pressures, the pressure at D and the pressure at E. So the pressure at D will just be the sum of all the pressures above it. So there's going to be a pressure due to a moving fluid, and we'll just call that either PB or PL because we're saying this is Z equals L and this is Z equals 0. So this will be PB or PL. So the pressure at D equals PB plus rho times G times B minus C, which is just this height, B minus C, and then rho, the density of the CCl4 times G times H. Well, this is going to be like capital H. These H's are not the same. This is just like a typo with this edition of the book. This should be like capital H, like if you don't hear it, capital H. This is capital H. I don't know why in this book it's like a typo here, but yeah. So the pressure at G is PB plus rho G B minus C plus rho G CC L4 times capital H. And then again, this is capital H. And then the pressure at E, which is equal to the pressure at D, equals rho G lowercase h, which is just this, and plus rho G BC again, because B and C is the same as this distance here. And then plus rho G H, rho G, this big H here. So yeah, you'll be able to cancel these two distances on either side of the equation. So yeah, this is the pressure. This side of the equation is the pressure it's the pressure here, or the pressure here, I'm sorry, this side of the equation represents the pressure at D, and the other side of the equation, this side of the equation, represents the pressure at, here's the correct thing, pressure at H, or pressure at E, sorry. And you can set these equal because there's an equal amount of fluid below each of them. So now what we're trying to do is basically just convert these pressure terms into modified pressure P0 minus modified pressure PL. And that's just because that's a form that you often see in these velocity equations. You'll see modified P0 minus PL. And modified P0 minus PL equals P0 minus PL plus rho GH. And you could see a bunch of proofs and like problems for that. But basically, just to solve for that, I'm basically just isolating P0 minus PL plus rho GH. And there's rho GH. These terms cancel. And yeah, basically you're just left with this. So you're just manipulating this equation here to get this form. And above expression allows us to calculate the modified pressure, P0 minus PL, and that equals that. So, all right, so here's like a tiny little explanation of that equation where I just kind of said that they're equal to each other. So yeah, this is the equation where I said where this can set, and then it was the equation. So yeah, it's basically, that's what I wrote. And then from page 84, you can see that the modified pressure equals pressure plus rho GH. And from that, we can say modified pressure 0 minus modified pressure L equals pressure 0 minus pressure L plus the pressure plus rho GH, and this H is at pressure 0. So at P0, the height is H. And at PL, we could say the height is 0, and that's like by comparison to H. So the pressure at 0 is H above the pressure at L. So we're just basically it's like a difference between the two, so you don't have to have like actual values. Like you're subtracting one value from another, so it doesn't need to be absolute values. It can just be values that are going to be the same distance from each other, and that distance is H. So H equals 0, so minus rho G at H equals 0, which it's not really 0, but it's just it's probably like H equals well, yeah, I guess it's just H equals 0, pretty much. So then you can take this equation, so this term will just cancel out, basically. So you just multiply this here by L, and I'm just doing this manipulation to show you that how I actually went from here to here, or here to here, and then back to here, because this equals this. So yeah, I multiply by L, and I just cancel these R's out just to make the algebra look better. So then, yeah, sine theta times L equals H, And that's because the drawing is like, well, capillary. Sorry, setup is kind of jank. It's like, this is where the liquid flows down here. The angle is theta. And so this length here is L. So, where is it? Sine theta times L equals, and this is H. So sine theta L equals H. And that's where we get that. Sine theta L equals H. And then, so from that we could say, we just basically replace this with this and all the canceling out, and we get this. And that just proves that this expression equals the modified pressure P0 minus PL. So yeah. All right, back to the Google Drive. So yeah, from this we get this expression, and that's because we're inserting this for this into this expression here. So we get this derivative equals this function here, and that, yeah, that's what you get. So now with this expression, we can see that we don't need lowercase h, and we don't need theta, because obviously those terms aren't present because we set h equal to other things, and we were able to get rid of that term. All right. So assuming we have a radial coordinate system, we're going to do the boundary conditions. And again, we having a radial coordinate system because it's a cylinder, or cylindrical coordinates, we're using a cylinder. Obviously, that makes sense. At the radius equals 0, dvz dr equals 0, and that's because the derivative, or that's because the max velocity is in the middle of the pipe, and that's because the wall on either side of that max velocity slow down the velocity. So at the location that's farthest away from the at the location that's farthest away from those boundary conditions where the velocity is 0, that's where the velocity is going to be at the max. And the derivative of a max is always going to be 0 because the derivative, or a max, is like a hill. It's like the top of a hill, and if you have a line that's perpendicular to that hill, which is going to be the slope, that's going to be a horizontal line, and the slope of a horizontal line is 0 because slope is y over x, and the y of a horizontal line is 0. All right, so the second boundary condition at r equals big R, the velocity is going to be 0, and that's the law of the wall boundary condition. And that is because we're assuming static friction at the wall. So as long as the liquid is laminar, we're assuming like complete static friction at the wall. So the water at the wall is completely stopped, and it moves at the same speed as the wall. So that's why velocity is 0 at the wall. So now we're going to integrate twice. We're going to integrate this equation twice. So separate and integrate first, multiply the dr over, and separate and integrate. So integral of dx is just x. So the integral of this, integral of d, whatever this is just going to be this. And obviously pretty standard integration here. Integral of r is just r squared over 2. So, and you have the extra integration constant, you only have 1, and that's because you only need 1, because technically there's going to be 1 on this side and 1 on this side, but you can just move them over to both to one side because they're both just constants. So now isolating the derivative, and that's because this derivative is going to be our second boundary or our one of our boundary conditions. So at r equals 0, dvz dr equals 0. So yeah, so we set this equal to 0, and we set this equal to 0, and then we solve for c1. And we see that since there's a 0 in the denominator here, c1 also has to be 0, because if it was anything else, it would just go to infinity. So we just assume that it's 0. Because if it wasn't, the whole equation would just blow up and just not work at all. So c1 just has to be 0. All right, so integrating a second time, integrating this equation a second time, and this is going to be 0. So it's going to be pretty simple integration. Yeah, just the integral of negative r is negative r squared over 2. And yeah, that makes sense. So we're using the second boundary condition now at r equals big R, vz equals 0. And by the way, if you have a derivative boundary condition, you're always going to want to do this boundary condition like mid-integration. You'll have to do it mid-integration. So yeah, that's just a little note there. But yeah, at r equals big R, vz equals 0, wall to wall. So applying that boundary condition, setting vz equals 0, setting little r to big R, and then we solve for c2 by isolating. So yeah, that's pretty easy in this case. And then we just plug c2 back into this equation here and simplify. And I think, no, it doesn't give you an answer, but I just kind of simplify just to get it into the form that a lot of the problems want you to get it into. Obviously, you can just leave it like this if you want. But I think the problem is actually asking for a mass flow. So what is it asking for? Yeah, mass flow. So yeah, we're going to need to convert this to a mass flow equation. And for that, we're going to first need to find the average velocity, because mass flow is just average velocity times rho times cross-sectional area, I think. But yeah, okay, so average velocity is just the integral of vz over dA, which is the differential area perpendicular to the velocity direction. And A is also the area perpendicular to the velocity direction, but it's not differential. So this is the area perpendicular to the velocity direction. So this way, area equals pi r squared, and then dA is the same as AZ, because AZ is the area perpendicular to z direction, and we solved that earlier, I think. This problem. Yeah, AZ equals. So yeah, that's why I still went through with doing this, I guess, maybe. AZ equals 2 pi r dr, which is the same as delta r. There's some drawings there down here too. And yeah, there's the two rings that are expanding out as delta increases, or as r increases and delta moves the ring along with it. So yeah. So yeah, we're just differentiating in a range. Since we're using dr, we just need to cover the whole range of the radial direction, which is from 0 to r. So that's why our bounds are from 0 to r. And we just plug in our vz equation. Just plug this in. So first we take out any terms that are not like directly related to little r. And that's just all of this, and 2 pi. And that's just anything you can divide or like take out of the parentheses by like division or multiplication. generally don't try with addition or subtraction. Like there's some cases where I think you can do it, but usually it's pretty easy to mess up. So I just wouldn't do that if I were you. So yeah, I'm just taking out all those terms, calling this alpha because I don't want to write all this 1,000 times. And we're just doing the integration. It's pretty simple there. It's math. Just look at it. I don't know. Yeah. Yep. So yeah, mass flow then equals the average velocity times the area times the density. And that's because velocity is meters per second, area is meters squared, so that's meters cubed per second, and then rho is kilograms per meters cubed. So the kilogram stays, but the meters cubed of each of these two terms cancels out. And this whole conglomerate here is also volumetric flow, which is meters cubed per second. So yeah, so here we're just multiplying volumetric flow or no, we're multiplying the average velocity times the area, and then this whole parenthesis term is volumetric flow, and then we're multiplying by rho. And yeah, so we just get this. So this is our mass flow rate. So now we can insert our known values to find mass in SI, because I hate using United States units because they're just terrible. I hate it. Hate it, hate it, hate it. Okay. So yeah, it gives us the density of CCl4, 1.594 grams per centimeters cubed, and that equals 1,594 kilograms per meters cubed. And that's SI units for density rho. Density of water is 1,000 kilograms per meters cubed. You should probably just know that. Viscosity of water, 0.0089 pascals seconds. I think it might give you that. I'm not sure. I've seen from values like in textbooks for like normal conditions from like 0.0085 to 0.009 to even 0.001. Some people use that. So yeah, here I just convert inches to feet to meters, and then I convert the radius. Again, these length and this radius is given in the problem. I'm just converting these to meters so I can just do that. And then h equals 1 inch, that's given, equals 2.254 centimeters. It's a pretty well-known conversion. Divided by 1,000 to get into meters. And then I'm plugging all these values in. And then if you use SI for all of the whatchamacallums, all of the values in equation, you can be assured that the result is going to be also SI. So the SI units for mass flow is kilograms per second. So yeah, 0.5568 10 to the negative, or e to the negative 10 kilograms per second. And it wants in lbs per hour. So we're going to convert that 2.2 lbs per kilogram times 3,600 seconds per hour. So yeah, this should be seconds here, but I just didn't put it. So yeah, I get 4.41 e to the negative 6 pounds per hour. And I think that's the problem. If you have any questions about other problems, please comment. If you have any suggestions about the videos, please comment. If you just have any random other questions, sure, comment that too. Please subscribe, I guess. Yeah, have a nice day. Bye-bye.